Next, we will discuss how to do calculus with the arc cotangent function. Let's consider the arc cotangent function and let's find its derivative. Of course, we can use the limit definition of the derivative, however, we get stuck quick. So let's try the implicit differentiation instead. First, we apply the cotangent function to both sides and then differentiate each side. On the left side, we use the chain rule, and on the right side, it is just the derivative of x. Divide both sides by the negative cosecant squared of y and replace y with the arc cotangent of x. We definitely learned how to simplify such expressions in trigonometry. So let's simplify this expression using the procedure developed in trigonometry. First, we introduce theta by labeling everything inside the parentheses as theta. The original expression is now very simple in terms of theta. But what do we know about theta? From its definition, we know the domain of theta and can produce the following statement. Next, we recall the definitions of both involved trigonometric functions, and now we can draw the reference triangle with theta in standard position and label the sides appropriately. We then use the Pythagorean theorem to find the missing side, and finally plugging the needed sides into the expression in question. After simplifying the trigonometric expression, we now have the following result. In summary, we now have the formula for the derivative of the arc cotangent function, as well as the formula for the antiderivative of its derivative. Now we can find the derivative of the following function. We start the process by recognizing that we have to find the derivative of a composition of the arc cotangent function applied to the reciprocal function, which is equal to the following expression, in which we know how to find all the components. We get the final answer after simplifying. Let's do another example. We start the process by recognizing that we have to find the derivative of a composition of the power function applied to the arc cotangent function, which is equal to the following expression, in which we know how to find all the components, and we don't need to simplify anything here. Let's do an example of integration. We first recognize the pattern and rearrange the integrand. Then we set up the substitution by setting a new variable, let's say t, equal to the arc cotangent of x, and finding the differential of t. Next, we plug everything into the original integral and notice how, because of the discovered pattern, we have nothing but the function of t left in the integral. We finish the process by finding the antiderivative and plugging the original function arc cotangent back for t. If you're familiar with the derivative of arctangent function, then you are probably noticing that we now have two expressions for the same indefinite integral. How is this possible? The reason is the cofunction identity for inverse trigonometric functions that states that arctangent of x plus arc cotangent of x is equal to pi over 2, which means that the negative arc cotangent of x is the same as the arctangent of x, but they are pi over 2 units apart. So it doesn't matter which antiderivative you will use. Let's do an example of a linear substitution. We set up the linear substitution by setting t equal to 2x and finding the differential of t and expressing dx in terms of dt. As a result, we have a simple indefinite integral in terms of t. We continue with the integration process by finding the antiderivative and replacing t with the original function. Alternatively, we could have finished the problem by using the arctangent function as the antiderivative. Both answers are correct. We discussed how to differentiate and integrate the functions that have the arc cotangent as one of their components.